welcome to the day 5 of first week. So, in the last class we started looking at how laser to learn how laser works, or in other words the principle of laser action. So, in learning principle of laser action, we started looking at interaction between light and matter, taking simple example of an atom and taking only two levels, two energy levels. So, constructing two level system, and we learnt about different optical transitions. So, what are the optical transitions that we learned? We learnt about absorption, we learnt about spontaneous emission, and also we learnt about stimulated emission. We also learnt why there was a need to bring in this concept of stimulated emission, which was done by none other than Einstein. So, we also learnt about the rate laws governing these optical transitions, this absorption and both the emission processes. So, after looking at their rates, we brought in the principle of detailed balance, and thereby we equated the total rate of absorption to the total rate of emission, which includes spontaneous and stimulated emission. So, what we had? We had total rate of absorption equal to total rate of emission, correct. So, we started looking into the mathematical relation. So, we know what is the total rate of absorption, and that was given by B12. So, just to remember, so this is state 1 and this is state 2, okay. This having energy E1, this having energy E2, and the number of atoms are N1 and N2 in these two levels, okay. So, we are considering only two level systems. So, the absorption was given by B12 multiplied by N1 multiplied by rho H nu 12. That was our formulation, and we equated it to the rate of spontaneous emission given by A21 multiplied by N2 plus the rate of stimulated emission, that is given by B21 N2 into the photon density at frequency nu 12. Okay. So, we are going to use this one to see how actually Einstein brought his model of black body radiation, where he assumed a black body to be constituted of several such two level oscillators as we have shown here, and see if we can come to Planck's law, okay, which it should be. So, now if we rewrite this one as A21 by B12 N2 by N1 plus B21 by B12 N2 by N1 multiplied by rho. Okay. So, now what we need to do, we need to take this part on the left side, and because both of them have this term rho, and take this rho outside, so that we can get a final expression for rho. So, if I do that, will be equal to A21 by B12 multiplied by N2 by N1. Now, I have taken this part on this side. So, this minus this part, taking rho out of the bracket. So, I have 1 minus this part, correct. So, now that part is now going to the denominator. So, then I have 1 by 1 minus B21 by B12 multiplied by N2 by N1. So, if I just rewrite this one, it will be A21, and for the time being let us take this B12 here. So, it will be N2 by N1 multiplied by B12 minus B12 into this quantity. So, it becomes B21 into again N2 by N1, right. This is equals to my rho. Now, if I know Boltzmann distribution of partitioning the number of atoms in different levels, different energy levels, then for our two level system that we just discussed, N2 by N1 is equal to e to the power minus delta E by kT, where k is the Boltzmann constant. And in our case, this delta E is E2 minus E1, which is equal to h nu 12. So, I can write this one as e to the power minus h nu 12 divided by kT. So, now if I take this value of N2 by N1 and replace it here, I will get an expression in terms of that exponential term, right. So, if I just rewrite here, so again rho h nu 12 equal to, if I look at there, so I have A21 multiplied by N2 by N1. So, I will use this value. So, by kT, then in the denominator what do I have? I have B12 minus B21 and again multiplied by N2 by N1, which gives me minus h nu 12. So, I can omit using this subscript 12 henceforth, and I can just write h nu. Okay. We will know what nu it is actually, right. So, now so at this point, if I divide both numerator and denominator by this quantity e to the power minus h nu by kT, then what do I get? I get A21 divided by B12 divided by e to the power minus h nu kt. So, it becomes e to the power plus h nu kt, and I am not writing this 1 2 anymore. This minus only b 2 1. Fine. So, this is my rho value. Now, Einstein wanted to come to Planck's law. Okay. So, now he got this one. So, I will write it again h nu 1 2. Now, at this point you recall what Planck's law was. Okay. So, that we mentioned in the last class is the spectral density at a particular frequency, that is our nu 1 2. So, that was given as it was given for a black body which is in thermal equilibrium at temperature T, was given by 2 h nu cube by c square, where nu, as usual, you know the frequency of the particular light of the spectrum that we are considering. C is the velocity of light, h is the Planck constant, multiplied by 1 upon e to the power h nu by k t minus 1. So, this was Planck's law. Now, if I want to compare what Einstein derived and what Planck had derived, then we can see that they are very similar, and actually this particular equation boiled down to this Planck's law under certain conditions. So, what are the conditions? Let us look at that. So, let me wipe this part. All right. So, as I was saying, this will boil down to this expression, when if you look at, if B 1 2 becomes equal to B 2 1, then, and if A 2 1 by B 1 2 or B 2 1 is a constant. So, let me mark this one. So, this expression I am putting as 1, and this Planck's one I am putting it as 2. Then 1 goes over to the form 2 has when B 1 2 is equal to B 2 1 and A 2 1 divided by, say, B 2 1. Okay. So, these two are equal. So, I can take any one of them. So, here is equal to 2 h nu cube by c square. If you use these two, you will see that this equation 1 and 2 are identical. Now, there are very interesting things to notice here. Okay. Suppose I mark this one as 3 and this one as 4. Then from 3, what do I see? B 1 2 and B 2 1 are equal. So, from equation 3, it tells me what is B 1 2? B 1 2 is the rate constant for absorption, and B 2 1 is the rate constant for stimulated emission. So, in other words, I can say the rate of absorption is equal to the rate of stimulated emission. This is a wonderful outcome. Okay. What it tells is that at a given condition, if I have certain population of state 1 and state 2, and if I come with a light that has a frequency such that h nu matches with the delta E, then the amount or the number of molecules that will go from state 1 to state 2 will be equal to the number of molecule coming down from this one to this one. Their rates will be same. Okay. So, this is what we see here, and actually if you think about it, this can be a problem in having laser action. Why? We will see it in a while. Just remember, laser deals with the stimulated emission, and it actually based on the amplification of the stimulated emission, right. So, the radiation coming out due to the stimulated emission, if you can amplify, you can get a laser. Now, if some other process has the same probability of happening as that of the stimulated emission, then that certainly poses some problem to you. Okay. Now, if we look at this equation 4, what does it tell me? A21 is the rate of spontaneous emission, B21 is the rate of stimulated emission. I want to have my system to give more stimulated emission and minimize the spontaneous emission, because I want to utilize the stimulated radiation, correct. So, what I need to have, if I need to really get a laser, that this quantity A21 by B21, this ratio, so this needs to be minimized. Right. So, how can I do that? I can either make this stimulated emission, spontaneous emission rate constant very low, and making B21, that is a stimulated emission rate constant, very high, right. So, how can do that? We will see that very soon. Now, just look at this right hand side of this expression. What do I have here? I have constants except the quantity nu. So, nu is more, meaning this ratio is more. I do not want this ratio to be high, I want this ratio to be low. Now, if I go and increase this frequency, so if I go from say microwave to infrared to visible to ultraviolet to X-rays, the probability of spontaneous emission will be much more compared to stimulated emission. Thereby, my job will be very, very difficult to achieve laser action at that high frequency compared to a lower frequency. And if you remember my first class where I mentioned this, that getting to lasers at a higher frequency is a very challenging job. And that is one of the reasons that people struggle to get lasing action in the optical frequency. And you remember, at the microwave wavelength region or microwave frequency region, this kind of amplified emission of stimulated radiation was already achieved, and that was called measure, right. So, measure was already there. Laser or optical measure, that term that time people used, came much later. because it is not easy to handle this ratio as you increase this one, correct. So, what I said in the first class is now well explained. All right. Now, we have learned to some extent about the stimulated emission and you know how we can possibly increase the stimulated emission. Now, just let us consider at this point the two-level system once again. So, what we do, let's consider a system where the molecule is excited here, and then I am coming with a photon matching with this energy gap, and this comes down emitting 2 photons. Now, what are the properties of these photons that are coming out as stimulated emission that we can get from this behavior and learning whatever we discussed so far. So, the first thing that we can say that for this system, the stimulated emission will give me photons with or will give me the photons that will have same energy as that of the incoming photon. So, this is same h nu. Now, from this interaction, so if the photon is coming, so this will go, it will also take the outgoing photon that is actually coming due to emission along with it. So, their direction is the same. So, the outgoing photon will have the same direction. So, if I write the direction of the photon by the wave vector k, then k is same as that of the incoming photon. And this photon is coming and interacting with this instantaneously, the light is being emitted and the original light is also going. So, there is no option for the emitted light to have a different phase. That means that both of these photons will have the same phase or they will be coherent. Okay? So, suppose there are many atoms excited here and I am coming with n number of incoming photon and there are 2n number of outgoing photons, then those 2n photons will be coherent. Okay. So, third is the same phase. So, phi is identical. So, same energy, same direction and same phase as that of the incoming photon. Now, these are a set of a very wonderful properties, right. So, these properties are of our interest because if I can use the stimulated emission with these properties and we can amplify it, then we get a source of light which has a very high energy and the property as written here, that is they are of same frequency. So, there will be only one frequency of light coming out, that means they will be monochromatic. They will have same direction, so they will have a directionality, they will act as a beam and they will be coherent. So, this is a wonderful thing, right. So, these are all interesting, correct. So, coming back to the question that after learning this stimulated emission, what is the condition when I can achieve laser action. So, we saw that this rate of stimulated emission, correct. So, stimulated emission by rate of spontaneous emission, this I can write it like B21 into rho. So, I am not using that h nu 12 just for simplicity. So, B21 sorry by spontaneous emission, that is A21 into, okay. Sorry, rate of, I am sorry. So, I should write this is not spontaneous emission, but this is absorption. Of course, we have to minimize the spontaneous emission, but also I have to do something with this ratio of rate of stimulated emission to that of the absorption, because I want to have more stimulated emission, and if absorption and stimulated emission are equal, then I will never be able to achieve the condition of lasing, right. Lasing means which lays, or when it lases. So, let me correct this one. So, this one is B12 in 1 rho. So, from that expression 3 we have seen from Einstein's formulation that absorption and emission stimulated emission rates are equal. So, therefore, it becomes like essentially N2 by N1. Now, when this is less than 1, this ratio, so rate of stimulated emission by rate of absorption, which is ultimately is N2 by N1, if it is less than 1, then what do I have? I have a system where absorption dominates. So, here absorption dominates and I have no luck with laser action, right. I have to get stimulated emission, use a huge amount which I will amplify and get to get a laser. But here if the absorption dominates, then most of my light will be only used for absorption. I will never be able to get maximum output or stimulated emission. If it is equal to 1, then again my situation is same, that the rate of absorption and the stimulated emission remains the same. Okay. So, I have a condition of saturation. So, the number of photons that I am putting, it is not leading to anything, because the number of photons going up, number of photons coming down due to stimulated emission are exactly equal. So, there is no net gain. So, this is a term that will be very, very important to you. I must gain something, right. So, what I am spending and my earning should be much more than that. Then only there is a ultimately we can get light output which is much more energetic. If I have to supply more than I get, then there is it has no importance. So these two conditions is not going to lead me anywhere close to having laser action. But if I have a condition such that n2 by n1 is greater than 1, what I have? I have a condition where stimulated emission, it dominates. And the moment stimulated emission dominates, my job is pretty much done. I have got a system which gives me much more stimulated emission, and I can take that stimulated emission, amplify it and get a laser output. So we will stop here today, and in the next class we will go into the more detail of how laser can work, how can I utilize this condition to get a laser. So thank you very much.